Greetings, everybody, and welcome to the latest edition of the Physics Corner. I'm your host, Dr. Christopher Sorolla, and this is a video series in which we set up and solve interesting and simple physics problems for introductory classes. Today, we're looking at the electric field from two different similar situations. One is a conducting sphere of charge, and the other is an insulating sphere of charge. So, what do we mean by this? Let's assume that somehow we have managed to place charges equally distributed throughout the spheres. Both of them, by the way, solid, uniform spheres. Let's make that clear. And let me draw this over here first for the insulating sphere, and you'll see why I'm doing it over here first in just a moment. So this will represent the idea that the charges are evenly distributed throughout the sphere. Now, insulators, by definition, do not allow charges to move. So once the charges are placed equally distributed throughout the sphere, they're stuck in place. They don't go anywhere. But what about a conducting sphere like this? Let's suppose I start it like that. What's going to happen to the charges? Well, these charges are all positive signs. Notice they're all the same sign, and like signs repel each other. And because it's a sphere, they're going to repel each other as best as possible, meaning that we will all end up on the outside skin, if you will, of the sphere. So the conducting sphere, the charges end up over here instead of being distributed inside. So even though you start, or could start, at least in theory, putting all the charges inside the conducting sphere, because conductors allow charges to move freely, those charges will repel each other and they will go as far away from each other as they can possibly get, which means they'll be evenly distributed on the outside of the sphere itself, or the skin of the sphere, if you will. All right, let's go ahead and take a look at our charges then and our fields. So if we want to talk about the case of the conducting sphere, let's sketch that again like this. And let's again sketch our charges on the outside of it. Now these little charges are meant to be on the actual exact surface of the sphere itself, but of course that's kind of hard to draw that way. Let me put a little letter, or capital letter Q, right next to that to represent the total amount of charges present. We can measure the amount of charge in two different places. One is at a distance like this. We'll say R over here, from the center of the sphere to some point still inside the sphere. Another, a distance like this, R over here, which is definitely outside the sphere. Also, let's note that the radius of the sphere, as given, is capital R. So what does this mean? Well, the general formula for electric fields like this would be KQ over R squared, right? That's the general formula that you have. Now, this means specifically the charge that's inside any particular volume of space, okay? So if you have this going on, then you can have this field. So let's see. Now, let's do the outside first because it's easier. So if I say draw a spherical shell around this, I don't have to draw the whole thing. You can kind of hopefully get the idea. If we're at this distance, then outside, or if you prefer R greater than capital R like that, notice that all the charge Q is contained inside there. So the electric field is KQ over little r squared. That's simple enough. Which is another way of saying, by the way, if you have a sphere of charge and you're outside of it, the field that you get looks like the field from a point source. Looks exactly like that. What about the inside? It's a little trickier, but it's also doable, of course. Little r less than capital R, in other words. And that would put us right about here, right? Now, notice something interesting in this little shaded area. There are no charges. None whatsoever. Which means Q is 0. Q inside is 0, which means the electric field is 0. This is an interesting statement, by the way, to make. This is one of those rare cases where we have what we call a discontinuity. In other words, the value of something usually doesn't change abruptly like this. It usually has even if it looks like it's a swift transition, it's usually still a smooth transition if you look at the details. That's not the case here. There's an actual very distinct transition when you get to the surface of the sphere. Now, the surface of the sphere itself does have the charges on it, so we could officially make this statement like this, where little r is the greater than or equal to the radius. In other words, since the charges are on the radius of the sphere, that also counts. So this is your results. Now, if I plot this, excuse me here, make sure we get this centered again. Let's suppose that this is the electric field and this is the distance from the center. Let's go ahead and mark the radius right there, for example. And let's mark this as KQ over capital R squared, like that. We'll notice something kind of interesting happens here. The field has a value of 0, which I can illustrate something like this, all the way until we get to the radius of the sphere. At the radius of the sphere itself, where little r equals capital R, this and this, the capital R and a little r are the same thing, and then from this point downward, the field drops off as the square of the distance. It looks something like that. So that gives you kind of a funky feeling, if you will, as to how the field behaves. But it's true, this works. Okay, this works because the charges restrict themselves to the outside skin, if you will, of the sphere. So that is the case of the sphere that's conducting. All the charges move to the outside, therefore the electric field is 0. By the way, here's another way to quickly think about why that field might be 0. Take a look. Suppose that we ask about the charge from the field from just this charge alone. That will give us, of course, an electric field that goes off equally well in all directions, right? But notice there's a charge over here exactly opposite of it on the other side of the sphere. And this charge will send an electric field line also towards the center. But something that you've probably learned by now is that electric fields can't cross each other, right? That's one of the rules for electric fields. In order to do that, they must avoid each other. Well, not only do we have these two, say, repelling each other, so to speak, but then this pair of charges will repel each other, and so will this pair, and so will this pair, and so on. In fact, every charge will have the same issue, and the only way to avoid having any electric field lines crossing each other inside the sphere is to have no electric field lines in the sphere at all. So that's what we get for this particular case. All right. So what about the next case? What about the field of an insulating sphere where the charges are evenly distributed? And that is a little more complicated on the inside, but we can also do that. So let's take a look. Okay, so we're back, and let's go ahead and take a look at our insulating case. So again, the insulating case is the charges are evenly distributed out throughout the entire sphere. I've only got the inside drawn because that's the only part that is really difficult to talk about. So outside the sphere, it's the same solution as we had before. So if R is greater than or equal to capital R, like that, then the electric field is KQ over R squared. But what about inside? Inside's a little trickier, okay? So inside again is when little r is less than capital R, right? So how do we do that? Well, the key thing is to understand that the electric field is KQ inside, like that. This is the key idea, that is the charge that's inside. We already talked about why there was no electric field inside the conducting sphere, because there were no charges inside the conducting sphere. It's one way to look at it. And of course, there's other ways to look at it, like the electric field lines are repelling each other and so on and so forth. They all are equivalent ways of saying the same thing. There's a kind of an interesting trick you can do to try to figure out how many charges are inside a sphere like this, though, the one that has the charges evenly distributed. So here's an interesting idea that we're going to show you. It's called charge density. Now, you've probably learned about mass density earlier in your physics career, where it's the amount of mass per unit volume. Well, density turns out to be a useful term for all sorts of ideas. An amount of something divided by a amount of space, for example. And so not only can we talk about mass density, but you can also talk about number density, the number of items in a volume, for example. And you can talk in this case about charge density, the number of charges inside a volume. So let's do that. So charge density, and we'll be using the same symbol for density that we've used before. We're not doing mass density in any of this question, so we're not going to get it confused, is equal to the total amount of charge per unit volume, which I'll write like that. By the way, we're looking ahead a little bit. I'm going to write VOL for volume here, because capital V will end up meaning some other thing coming up very soon in your physics career, and let's not get that confused. So What about this case specifically? Well, this is a sphere, right? So it'll be the charge, which we already have given, divided by the volume of a sphere. And it's 4 pi over 3 times radius cubed, like that. Notice I'm using capital R because that's the radius of the cube itself. So the total amount of charges divided by the entire volume of the sphere. And that's the formula for the volume of a sphere. So that's called charge density, all right? Now, let's talk about the charge inside. Again, when little r is less than capital R, to make it specific, okay? Well, if we take this formula here and turn it around, we'll notice it'll be density multiplied by volume, like that still. But now it's volume for this, for little r, which is to say density, which is q over 4 pi over 3 r cubed. And now the volume of this is what? Well, it's the little r that we have to worry about. So imagine we draw a little sphere like this to represent the little r distance. And I'll just shade it to double emphasize that. Notice in this case there are charges inside here, right? That's what we're calculating, the charges inside this section here, okay? Now, of course, there isn't an actual boundary, right? We're not saying that, but we are saying mathematically, you can easily do this. So there is a volume of space defined by little letter r like that, and that volume is 4 pi over 3 little r cubed, like this. So that's the charge inside that section. Notice something else that we're doing, by the way. All these charges on the outside of that section don't count any more than they did in the previous example. Okay? So the charge that's inside that section of sphere, well, this is why, by the way, we didn't mess with the 4 pi over 3 part. Notice that 4 pi over 3, 4 pi over 3 cancel, so that section goes away. And it's the total charge, and then little r cubed over capital R cubed, like that. One more step to finish what we're doing. Again, our main formula is this for electric field, right? So electric field is K Q inside over little r squared. But we have a formula for Q inside, so let's apply that. So K divided by little r squared, and then Q, not Q inside, just Q now, r cubed over capital R cubed, like that. And now you can see a couple things happen. R squared here cancels out 2 of the r's here. We do have 1 r left over, by the way. And so we'll have a K capital Q R over capital R cubed on bottom like that. And that's our mathematical solution. So what does it look like if I graph it? Let's sketch out a graph quick to show that off. Again, let's do the same kind of thing. So electric field here versus radial distance from the very center of the cube. This will be the point where we have KQ over capital R squared, like that. Let's put capital R here and note what we have there. Okay, so if we're at the very center of the sphere, that's little r equals 0, then of course, no electric field. That makes sense. As we go further and further, as little r gets bigger, it gets more and more of a fraction of capital R. And notice also that K, capital Q, R cubed, those are all constant numbers. Those are all set values. So that's a constant. And we're just multiplying by that little r. Now, when we get to the surface of the sphere itself, that's capital R, then that's going to cancel. So let's show that. So at the surface of the sphere, little r equals capital R, right? And now the electric field is KQ capital R over capital R cubed, or KQ over capital R squared, like that. So what happens if we were to graph this is we start at 0, it goes up in a linear fashion, straight line fashion, like that, and it goes up all the way like this to this point here. After which we go back to the original formula, this one over here, just like we had the previous example, it looks like that. So again, there's an interesting case of a discontinuity here, right? The electric field is not smooth, if you will. There's a definite kink at it at the surface again. But in this example, there is an electric field inside the sphere, interestingly. Okay. So there's two separate cases we've talked about. We talked about the case where there are charges attached to the outside of a sphere that's conducting. All the charges rush to the outside and are stuck there. Therefore, the electric field is zero inside the conducting sphere. But in the case of an insulating sphere, we have the charges evenly distributed. You do have an electric field inside the sphere. In fact, the electric field starts at zero at the very center, but slowly grows until it reaches a maximum at the surface, and then in both cases drops off as the square of the distance outside the sphere. All right. Thank you, everybody. Technical assistance is supplied by Sidney Galtraw and Sophia Turner. Funding for these programs comes from the University of Mississippi and University of Southern Mississippi. I'm your host, Dr. Christopher Sorolla. Thank you, everybody, for your attention, and clear skies, everybody.